In this lecture, we will be studying the unsymmetrical fault analysis. We know the different unsymmetrical faults: the single line to ground fault, line to line or double line fault, and double line to ground fault. So first of all, we will be studying the single line to ground fault. How to analyze a single line to ground fault. What will be the equation for fault current in case of a single line to ground fault? So let us see. So for that, consider an unloaded alternator whose neutral is grounded through an impedance Zn. So this is the equivalent circuit of an alternator. Its neutral is grounded through an impedance Zn. Let a single line to ground fault occurs on phase A through a fault impedance Zf. So we are considering an unloaded alternator. So terminals are not connected. So under this condition, let the phase A conductor be grounded through a fault impedance Zf. So there is a short circuit fault at phase A. Phase A conductor is grounded and there is an impedance Zf, a fault impedance Zf in the ground path. So this is a short circuit fault, a single line ground fault. So when phase A is getting connected to the ground, a current will flow from phase A to the ground, and that is our fault current If. Okay. So there will be a fault current flowing through phase A towards the ground. Now we can write the boundary conditions for this system as currents IB is equal to IC is equal to 0, because the alternator is unloaded, because it is not supplying any current. So terminals B and C, phases B and C are open, and IB is equal to IC is equal to 0. So this is one condition. Now when phase A is getting grounded, the current flowing through phase A will be equal to the fault current. So we can write IA is equal to IF. And one more condition, we can write the equation for VA, this voltage between phase A and the ground. VA is equal to IF into ZF. IF into ZF. It can also be written as IA into ZF, because IF and IA are the same. So these are the boundary conditions to be used for the derivation purpose. So now let us write the symmetrical components of phase A current. Symmetrical components of phase A current. Phase A current are, so symmetrical phase A current is IA. So its symmetrical components are IA0, IA1 and IA2. So using the matrix equation, we can write IA0, IA1, IA2 is equal to 1 by 3 into 1 A square 1 A square A into the phase currents IA, IB, IC. Okay. So this is the equation for calculating the symmetrical components of current. So but in this particular case, we got the value of IB and IC as 0. So let us substitute those values. So 1 by 3 into 1 A square 1 A square A into IA 0 0. So from this we can write values of IA0, IA1 and IA2. So we will get IA0 is equal to 1 by 3 into 1 into IA plus 1 into 0 plus 1 into 0. That is 1 by 3 into IA. Now IA1 will be equal to 1 by 3 into 1 into IA plus A into 0 plus A square into 0, which is again 1 by 3 IA. Similarly, IA2 will be equal to 1 by 3 into 1 into IA plus A square into 0 plus A into 0, which is again 1 by 3 into IA. So we got IA0 is equal to, IA1 is equal to, IA2 is equal to 1 by 3 into IA. Or from this equation we can write IA is equal to 3 times IA0. IA is equal to 3 times IA0. IA, which is also the fault current, IA or IF. IA and IF are the same. IF is equal to 3 times IA0 or 3 times IA1 or 3 times IA2. IA0, IA1 and IA2 are the same. So now this equation is important. We need it later. IA0 is equal to IA1 is equal to IA2. All the sequence currents are the same. They are having the same value. So now let us calculate the symmetrical components of phase A voltage. So symmetrical components of phase A voltage. So phase A voltage symmetrical components are VA0, VA1 and VA2. So we have already drawn the zero sequence networks, zero sequence, positive sequence and negative sequence network of a generator. So we know how to draw the network. And from the network we have already got the equation for terminal voltage. So from the zero sequence network we have VA0 is equal to minus IA0 into Z0. VA1 is equal to EA minus IA1 Z1 and VA2 is equal to minus IA2 Z2. Okay, so these are the equations for symmetrical components of voltages. Now minus IA0 Z0, keep it as such. Now look at this equation. VA1 is equal to EA minus IA1 Z1. So IA1 is equal to IA0. So replace IA1 with IA0. So this can be written as EA minus IA0 into Z1. So next is VA2. VA2 is minus IA2 Z2. IA2 is also equal to IA0. So replace IA2 with IA0. So this becomes minus IA0 into Z2. Okay. So now we can write the phase voltage VA as the sum of its sequence voltages. VA is equal to VA0 plus VA1 plus VA2. So we have voltage of phase A. VA is equal to VA0 plus VA1 plus VA2. Now we got VA0 as minus IA0 into Z0 plus VA1 is EA minus IA0 Z1 and VA2 is minus IA0 Z2. So we have substituted values for VA0, VA1 and VA2. So this can be written as EA minus, I am taking minus IA0 common. So minus IA0 into Z0 plus Z1 plus Z2. Z0 plus Z1 plus Z2. Okay. Now left hand side is VA, the voltage of phase A, and it can be written as phase A voltage. We have already written the equation for phase A voltage. VA is equal to IF into ZF and IF is equal to 3 times IA0. So let us substitute those here. So VA is, we can, instead of VA, we can write IF into ZF. And IF is 3 times IA0 into ZF. So let us take this term containing IA0 to the left hand side. Then it becomes IA0 into Z0 plus Z1 plus Z2 plus 3 ZF. And on the left hand side, it is the voltage source EA. So I have taken this term to the left hand side, and then IA0 is taken common outside. So this will be the equation. Then from this we can write the zero sequence current IA0 is equal to EA divided by Z0 plus Z1 plus Z2 plus 3 ZF. So we got the value of zero sequence current IA0. Now we know that IA0 is equal to IA1 is equal to IA2. So we got all the sequence currents. So what we need is the equation for fault current. So we know that the fault current, we already have a relationship between fault current and sequence currents. Fault current IF is equal to 3 times IA0, which is equal to 3 into this term. That is 3 EA divided by Z0 plus Z1 plus Z2 plus 3 ZF. So this is the fault current IF. So this is very important. This is the equation for fault current in case of a single line to ground fault through a fault impedance ZF. Okay. So now we have to draw the sequence network corresponding to the single line to ground fault. We have calculated the equation for fault current. We also have to draw the sequence network. So for that, we have a relationship, that is IA0 is equal to IA1 is equal to IA2. Okay. So all the sequence currents are the same. Current means current flowing through zero sequence impedance is equal to current flowing through the positive sequence impedance, which is equal to current flowing through the negative sequence impedance. So current flowing through all the sequence impedances are the same, means these three sequence impedances are connected in series. That is why current flowing through them are the same. So we can draw the three sequence impedances in series. So the sequence network corresponding to single line to ground fault becomes, so this is the positive sequence network, then the negative sequence network, and then the zero sequence network. All of them are connected in series. So positive sequence network Z1, voltage source EA, negative sequence network will have the negative sequence impedance only. Similarly, zero sequence network will have the zero sequence impedance only. Okay. Now, terminal voltage is VA1 in case of positive sequence network, VA2 in case of negative sequence network, and it is VA0 in case of zero sequence network. Now, let's see Z0. It is the total zero sequence impedance in the zero sequence network. And what will be the value of that? See, we know that this neutral grounding impedance Zn will appear in the zero sequence network because the zero sequence currents IA0, IB0 as well as IC0 flows through this neutral grounding impedance Zn. So 3 Zn will appear in the zero sequence network. So total zero sequence impedance Z0 will be equal to 3 Zn plus Zs. The zero sequence impedance per phase of the generator plus 3 times the neutral grounding reactance. So this will be Zg0 per phase, zero sequence impedance per phase of the generator plus 3 times Zn. that is total zero sequence impedance Z0. So now we got the network like this. Now, so current flowing through positive sequence network is IA1, this is IA2, and this is IA0. Okay, so the network is not complete. So let us see the equation for IA0. IA0 is equal to I is equal to V by R, V by Z format. So voltage source is EA, which is present here, divided by the total impedance include Z0 plus Z1 plus Z2 plus 3ZF. So one more impedance is there. IA0 is equal to a total voltage divided by a total impedance. So total impedance includes Z0 plus Z1 plus Z2 plus 3ZF. So Z0 plus Z1 plus Z2 is already here. So we have to add one more impedance, that is 3 times the fault impedance ZF. So it will be like this. 3 ZF. Okay. So this is the sequence network corresponding to a single line to ground fault. So now we have to consider some special cases also. So case 1 is a direct or bolted, a direct fault, also known as a bolted fault or a solid fault. Say a direct short circuit or a direct line to ground fault or a bolted fault or a solid fault. What is that? So it is the fault when phase A is getting directly connected to the ground without a fault impedance. So if a particular phase is grounded or connected to the ground directly, it is known as a direct fault, a direct short circuit fault or a bolted fault or a solid fault. So in that case, ZF will be 0. Here there will be a direct short circuit. So in that case, ZF will be equal to 0, and when ZF becomes 0, the fault current IF becomes 3 times EA divided by Z0 plus Z1 plus Z2, ZF is 0. So this is the equation for fault current for a direct or solid fault. So now the second case is neutral is solidly grounded. Neutral of the alternator is solidly grounded. So here we have considered an impedance Zn in the neutral grounding path. So if Zn is absent, that is neutral is solidly grounded means Zn is absent. Neutral is directly connected to the ground. So that case Zn is equal to 0. Then total zero sequence impedance Z0 will be equal to the per phase zero sequence impedance of the generator. Now the third case is neutral is ungrounded. So what will happen if the neutral is ungrounded? So we know that all the zero sequence currents IA0, IB0 and IC0 flows through the neutral. So the zero sequence currents are returning to the generator through the neutral conductor. So if neutral is ungrounded, there is no path for the zero sequence current to flow. So in that case, zero sequence currents will not flow. The zero sequence network will be open. Zero sequence current will not flow. That is IA0 is equal to 0. So we got in this particular condition, we have IA0 is equal to IA0 is equal to IA1 is equal to IA2. So if neutral is ungrounded, zero sequence current is 0. So here IA1 is equal to IA2 is equal to 0 because these three sequence currents are the same for a single line to ground fault. And that means the fault current is also 0. Fault current is 3 times IA0. So these are the various cases. Now see the direct short circuit case. So in case of a direct short circuit, ZF is 0. Okay, directly short circuited. So there is a chance for this derivation to be asked as derive the equation for fault current in case of a direct short circuit between one of the phases of an alternator and the ground. So in that case, while you are deriving, here we have to show a direct short circuit. ZF should not be shown here. So here there should be a direct short circuit. Then VA will be the voltage across this short circuit, and that will be 0. ZF is 0, so VA will be 0. So while proceeding with the derivation, substitute 0 here. Instead of VA, substitute 0 here. So here it is 0. Then instead of 3 ZF, we will get 0. And finally, IF will become 3 EA divided by Z0 plus Z1 plus Z2.